So our final project, we designed a temperature control using the TMP-01 chip from the Analog Discovery Kit. So if we were to actually build an application of this in the real world, a great example would be a thermostat. So thermostat, what it does is you can set, let's say in the wintertime, you can set a temperature when you want the heater to turn on. Or in the summertime, you can set a temperature for when you want the AC to turn on. So in this case, we did something very, very similar, but we used LEDs. But before we actually go into what our circuit was, before we actually started to build it, we have to first understand what's going on inside of the TMP-01. So if you look, you can see that it does use a sensor and it creates an output voltage, which feeds into this hysteresis generator. And what this hysteresis generator does is it's actually great for quite a few things, but it's really great in applications like this because you could get a lot of feedback from this output voltage. It's a live reading, so it can kind of fluctuate back and forth. So what the hysteresis generator does is it creates, it kind of reduces some of that feedback, and it gives us a really clear output or input signal in this case that we can use to go between when it switches between two different thresholds, like in this case, where it goes to a window comparator. So hysteresis generator is really, really important. Otherwise, if we were to do this without it, we'd probably see that the LEDs don't really trigger when we would want them to, just because we'd get a lot of feedback and noise from that, from the voltage coming straight out of the sensor. So then you can see that the hysteresis generator takes the output signal, the output voltage, and it feeds it into the input pins or the input signals into what we have here, the window comparator. And the window comparator is exactly as that sounds. It just creates a threshold between a low voltage and a high voltage. And so what we can do is we can make a voltage bridge or a resistor divide in order to set what we want these voltages to be. These voltages also represent the temperature. So we can set at which point we would want our green LED or the red LED to turn on. So when it gets set, if the output voltage from our sensor gets to a certain set voltage that we set it to, I think in our case it's about 1.4 volts for the low, about 1.5 for the high. So if it gets at or below our low set voltage, then it would trigger the green LED. Or if it gets at or above our high voltage, it would trigger the red LED. So that's kind of the purpose of the window comparator, is to create that window at which we want our LEDs to be triggered, or if it were an actual application when we want the AC to turn on or when we want the heater to turn on. So we built these both separately. We built a separate hysteresis generator and a window comparator just to see how they behave when they're taken outside of the chip. And we did that in order to understand exactly what's going on inside of the circuit.
Hi guys, this is Zoe, and next I will presenting the hysteresis comparator, which is a comparator with the positive feedback that could cause some delay on the output voltage. And here you can see is our non-inverting hysteresis comparator, and this is the LT space simulation. For the non-inverting hysteresis comparator, here is our feedback resistance. We set it to 20 kilo ohms, and we also have a 3 volts input voltage here. And this is the simulation for waveform for this schematic. And here we have the blue line, which is the output voltage, and the green line is the input voltage. As you can see here, we have 4.1 voltage for the output voltage and a 3 volts for the input voltage. And according to our calculation, the lower threshold voltage is about negative 2.6, and in the simulation, let's zoom in. Here we got a negative 1.8 volts as the lower threshold voltage, which is a little bit off from what we got from the hand calculation. And here is the higher threshold voltage. According to our hand calculation, we got 2.06, and here we got 1.8 volts for the high threshold voltage. And we did a analysis for the values, which you can see here we got 8.7% off for the percentage error. And when the input is the lower threshold voltage, the output turn from positive to negative, and when it hits the higher threshold voltage, the output turns from the negative to the positive saturation voltage. And next, we will have some breadboard demonstrations for this non-inverting hysteresis comparator.
So here we are looking at the characteristics of a non-inverting hysteresis comparator. And we would expect that with a non-inverting comparator, we would expect that when the input voltage goes low, the output voltage also goes low. And we can see that here in the waveform. And then when the input voltage goes high, the output voltage also goes high. Looking at the XY plot, this is showing us the voltage transfer characteristic, which in other words is showing us the flow of the signal with respect to the threshold voltage. So here it's a little bit difficult to see, but the flow is actually going in a counterclockwise direction. So the x-axis is showing us the input voltage and the y-axis is showing us the output voltage.
Okay, so next I'm presenting the inverting hysteresis comparator. This is the LT spec schematic that we built. And here we have a voltage supply at inverting terminal, and a R1 and R2 forms a voltage divider at non-inverting terminal as a positive feedback. And if we run it, we can have a 8.2 peak-to-peak voltage for the output voltage and 6 volts for the input voltage. And according to our hand calculation, which the lower threshold voltage is calculated by R1 over R1 plus R2 times the lower output voltage. And for this one, we got negative 2.06, which in our schematic, we got negative 1.8. And for the higher threshold voltage, we have 2.6, and in the schematic waveform, we have 1.8, which caused the percentage error at 8.7%. And for the waveform, when the voltage is at the lower threshold voltage, the output voltage is turning from the negative to the positive. And when the voltage is at the high threshold voltage, the output voltage is turning from the positive to the negative. And next, we will have some breadboard demonstrations for this inverting hysteresis comparator.
And now looking at the behavior of an inverting hysteresis comparator, we would expect the exact opposite from what we just previously saw. So here we see that when the input voltage goes low, the output voltage actually goes high, and then vice versa. When the input voltage goes high, the output voltage goes low. Now looking at the XY plot, we can see the voltage transfer characteristic. and it's actually flowing in the opposite direction of the non-inverting. So this is going in a clockwise direction.
Next, I will presenting the window comparator for the idea of getting to know better how the temperature control works. So this is our schematic for the window comparator. We have two comparators here, and the upper one we connect the non-inverting terminal to the voltage supply, and for the lower comparator we connect the inverting terminal to the voltage supply, which is at 5 volts. And here we have a voltage reference at 5 volts. And since here is a 10 kilo ohm resistor, we expect a voltage drop at this point, which we can see here is 3.33 volts. And since we have another 10 kilo ohms resistor here, we expect another voltage drop at this point, which we got 1.66 volts at this point. So let's take a look at our output voltage and the input voltage, which we can see that when the voltage is at 1.66, the output voltage, which is presenting as the blue line, turns from 0 to 5 volts. And when the voltage is at 3.33 volts, we have the output voltage turns from 5 volts to 0 volts. And this is our result for the window comparator. And next, we will have some breadboard demonstrations for the temperature control.
For our temperature control system, we utilize the TMP01 chip, which uses the concept of a window comparator, as just discussed, and it senses the temperature and converts it into a voltage, which then we can convert into degrees Celsius. So with the window comparator, it sets a low voltage threshold and a high voltage threshold. And in our design, we have a green LED, which indicates the lower temperature threshold, and a red LED, which indicates the upper voltage threshold. So when the voltage drops below our specified voltage, the green LED is triggered. And when the voltage goes above our high voltage, then the red LED is triggered. In order to set the voltage threshold, we use a voltage divide in order to indicate what our high voltage is set to and what our low voltage is set to. And in this case, with the resistors that were available to us, we were able to set the low voltage to about 1.4 and the high voltage to about 1.6. This chip uses a rate of about 5 millivolts per Kelvin. So when we do demo, as you will just see in a little bit, you will see that the change in voltage is very, very minor. So for our high temperature, we set it to about 1.5 volts, but here you can see it is starting to flicker on at about 1.66 volts, which is a little bit higher than we anticipated, but because we don't have the exact same resistor values, this is as expected. And as it starts to cool off, it flickers, and it turns off at about 1.64 volts. For the low voltage threshold, we want it to turn on the LED at about 1.4 volts, but here you can see it is turning on at about 1.48 volts. As it continues to decrease, as the chip is getting colder, the LED is brightening, and it's pretty bright at about 1.48 volts.